We're going to cover some circle theorems in the next few minutes, but first, a quick recap. A subtended angle is the angle made by a line, arc, or object. Equal chords of a circle subtend equal angles at the center. Therefore, if the angles subtended by the chords of a circle at the center are equal, then the chords are equal. Angles in the same segment of a circle are equal. If a line segment joining 2 points on the circle subtends angles at 2 other points lying on the same side of the line segment, the 4 points are concyclic, meaning the points lie on a common circle and are therefore the same distance from the center of the circle. So, shall we move on to the theorems? The perpendicular drawn from the center of a circle to a chord bisects the chord in 2 equal parts. Here we have a chord AB on a circle with a center O, and a line drawn from here to the chord, intersecting it at a right angle at C. We will prove that AC equals CB. First, draw in the radii OA and OB. On triangles OCA and OCB, we know that angle C1 is equal to angle C2 because they are right angles. The 2 triangles also have a common side OC, and sides OA and OB are equal because they are radii. Therefore, the triangles are congruent to each other. And therefore, AC equals CB, and we have shown that OC bisects AB. The converse or reverse logic of this theorem is that the bisector of a chord from the center of the circle is perpendicular to the chord. We see here that AB is a chord of a circle with center O, and that OC bisects AB. We'll prove OC is perpendicular to AB. Okay, first join OB and OA, which are radii. Now, look at triangles OCA and OCB. AC equals CB because OC bisects AB. The 2 triangles have a common side, OC, and sides OA and OB are equal because they are radii. Therefore, the triangles are congruent to each other with all 3 sides equal. And angle C1 is equal to angle C2. But angle C1 and angle C2 are supplementary angles because they lie on a straight line. Therefore, angle C1 and C2 are each equal to 90 degrees. So we have shown that OC is perpendicular to AB. Equal chords of a circle are equidistant from the center of the circle. We'll prove this given a circle with center O and 2 equal chords AB and CD. We start by constructing the perpendicular bisector of AB and CD from the point O, applying the theorem that a perpendicular drawn from the center of a circle to a chord bisects the chord. Then join OA and OC, the radii. In triangle OEA and triangle OFC, angles OEA and OFC are equal because they are right angles. And we know OA equals OC because they are radii. CF is equal to AE because AB is equal to CD and these chords are bisected. Therefore, triangle AOE is congruent to triangle COF. So OE is equal to OF, which means that the chords have the same perpendicular distance from the center. And the converse of this theorem is chords that are equidistant from the center are equal in length. This circle has chords AB and CD, both of which have the same perpendicular distance from O. We need to prove that the length of AB is equal to CD. Join OA and OC, the radii. In triangle AOE and triangle COF, angles OEA and OFC are equal because they are right angles. and we know OA equals OC because they are radii. We also know OE equals OF because the chords are equidistant from the center. Therefore, triangle AOE is congruent to triangle COF. So AE equals CF. But we know OE and OF bisect AB and CD because the perpendicular from the center of a circle to a chord bisects the chord. Therefore, AB equals CD. We have shown that the chords that are equidistant from the center are equal in length. An interesting property which arises from the theorem about the perpendicular from the radius to a chord is that if we are given 3 points, we can draw a circle that passes through all of them. As long as they are not in a straight line, this will always remain true, regardless of where the 3 points are. A set of points which lie on a common circle are called concyclic. To find the center of a circle connecting any 3 points, you begin by joining 2 pairs of points. We'll call these lines AB and BC. Then construct a perpendicular bisector for each line. We know the perpendicular bisector of AB will go through the center of a circle to which AB is a chord, and that the same will be true for BC. So the point where they intersect will be the center of the circle, which we'll call O. The radius of the circle is the distance between the center O and any point on the circle. So if we set a compass to length OA and draw a circle, we should find it goes through the other 2 points. But can we show that this will always work and prove the theorem? That there is one and only one circle passing through 3 given noncollinear points. Let's start by calling the perpendicular bisector of chord AB JK and write this down as our first statement and reason. So, we know a circle exists with its center somewhere on JK because we know that the perpendicular bisector of a chord, AB in this case, always passes through the circle's center. We also constructed the perpendicular bisector of BC, which we'll call LM. And for the same reason just given, we also know a circle exists which has its center somewhere on line LM, the perpendicular bisector of chord BC. Right then, we know a circle passing through AB has a center on JK, and a circle passing through BC has a center on LM. So if a circle passes through all 3 points, A, B, and C, then the center must be on both JK and on LM. But we know that the line segments JK and LM intersect at one point only. Remember, we know that JK and LM are not parallel or lying on the same line because they are perpendicular to AB and BC, which are not on the same line. Therefore, we know that there is one and only one circle going through all 3 points. Now we've learnt about concyclic points, we'll return to this theorem, which you may have seen from previous lessons. If a line segment subtends equal angles at 2 points on the same side of the line segment, the 4 points are concyclic. We start with a diagram of line segment PQ and 2 equal angles S and R subtended by PQ on the same side of PQ. We need to show why these 4 points will fall on the same circle. Let's assume for now that they do fall on the same circle and draw in the circle. We know that any 3 of these points are concyclic, so P, Q, and S must fall on the same circle. If R doesn't fall on the same circle, then a point T on the line PR or an extension of the line PR will. Then we can say angle PSQ will be equal to angle PTQ because these will be angles in the same segment subtended by PQ. But we have been given that angle PSQ is equal to angle PRQ. So angle PRQ must equal PTQ. This is only possible if T coincides with the point R because they are angles between the same line segments. So we have proved that P, Q, R, and S lie on the same circle. This is called proof by contradiction. These are the theorems and converses we've just covered. The perpendicular drawn from the centre of a circle to a chord bisects the chord. Equal chords are equidistant from the centre. There is only one circle that can be drawn through 3 noncollinear points.